Hey, so really quickly, I'm going to just be going over the results and the analysis that I did on the mini project number 3, which goes over the LeNET style MNIST inference engine that we were tasked with building in HLS. So kind of the overall workflow that I went through here is I used PyTorch to generate weights and biases based on the software model, trained that model, and then extracted the weights and biases, and then I'm storing those weights and biases as header files in text format that then get read in via the test bench. So then when we want to do a HLS simulation, the test bench can inject those. And when we want to do a synthesis, that'll just take the top and the supplementary C++ files and use the HLS pragmas to then schedule and synthesize the code into RTL. So here, the supplementary.cpp here is mostly just my individual layer implementations. Top calls everything together, you can see here. And then the top H just includes the declaration and headers for everything. So really quickly, I'll just do a test run here. We'll do a quick test simulation to just prove that everything's working and that the model's classifying these objects correctly. So you can see once this finishes successfully, we will get, C has finished successfully. The predicted digit class is 0, and if you look right here at our test bench, we are entering image0.text. So it has successfully classified. And we'll look at a confusion matrix later to show kind of a more high-level view of how the overall model classifies individual digits, but this should show that it is functioning, at least at the simulation level in HLS. So now I'll just go quickly into the mini project presentation. So to kind of look at the area latency and throughput of the model that we're using here, it's important to kind of analyze these things, right? Because they're huge in terms of what FPGA you can target for a specific design, and what frequency you can run at. So here we're just comparing the performance across the 3 different numeric formats. The LUT and DSP counts you can see come directly from the HLS csynth utilization reports. So they're confirmed by Bravato's post-synthesis utilization report. And as expected, the INT8 uses the lowest LUTs and DSPs, INT16s right in the middle, and then floating point 16 is the more complex because it needs extra logic for the exponent handling and normalization processes and stuff like that. Latency, we can see, is also taken straight from the HLS performance report after the RTL co-simulation. And it's for the top function. So we're looking at the calls to the supplementary implementation. So all 3 designs are pretty much, within a relatively close margin of latency, right? 900, 900, and 950. Slightly more latency for the pipelined floating point 16 implementation, whereas the integer 16 and int 18 or int 8 don't require as much pipelining. So in general, right, we can see that resource utilization scales with more complex data type, and latency isn't really hit as strongly by that effect, but we can see there's a clear relationship to latency and data type used as well. So now the power, kind of the dynamic switching power analysis that I did, we found these values from the Vato's power report, which is found after running implementation for each of the data type HLS models. So the Vivado uses the post-route netlist and the switching activity based on the clock frequencies and based on the number of transistors to estimate the total dynamic power that will be used. And kind of based on what we just saw, right? INT8 uses lower resources and operating at a similar frequency, right? It's going to have lower dynamic switching power just because there's less LUTs and less transistors switching over time. But yeah, that trend is also increasing, right? Like floating point 16 is significantly more complex. We need logic to handle exponent, mantissa shifting, a lot more comparison going on. So a lot more logic and thus more switching power. So finally, to kind of go over the actual overall high level accuracy of our model, we can see here that in general, they're all very accurate, right? INT8, though, because there's less precision in that quantization for the data type, there is less accuracy. We see 98.62 versus 99.11 and 99.23 for INT16 and floating point 16. And then this confusion matrix for the LeNET MNIST is for the floating point 16 HLS implementation. I only generated one. But this shows kind of, right, that the model has a very high classification rate. For zeros, there's almost no outliers. And then for some of the more common numbers that look like other digits, like 7, there's a slightly more variance there. But in general, you can see that this trend where the true label matches the predicted label is pretty clearly followed here from this confusion matrix. So the accuracies that we found here, they're computed by running the HLS test bench over the set of the MNIST test images that we have. So we have a database set that I got from PyTorch. And as expected, int 16 and floating point 16 are pretty much the same, right? So for this classification job, right, we would not need the more complex logic provided by floating point 16. It would be smart to probably just go with integer 8 if we're resource constrained. Yeah, so in general, that's kind of the high-level explanation of the entire project, and then a little bit proof of the HLS implementation accurately classifying the digit class 0 here. And if you want, we can really quickly change this to image 5, which is an image of the 5 here, and I'll just do another run, and we should see that the model accurately predicts digit class 5 from this run. Give it a little bit of time. And boom. So the predicted digit class is 5 when we feed it in that correct number. This failed to open file for writing. Doesn't really matter. It's just for debug stuff that I was doing, but is not needed for the final answer. Okay. So that should clarify everything. Thanks. Have a good day, guys.